Welcome to a deep dive into general relativity.
Yeah.
Specifically, we're diving into Carlo Rovelli's book, General Relativity, The Essentials,
Okay.
and really exploring how Einstein kind of reshaped the way that we think about
Yeah.
space and time. So get ready for some black holes,
Great.
gravitational waves, and even a little taste of the mysteries of quantum gravity.
Exciting.
I don't know about you, but have you ever heard that saying, time flies when you're having fun?
Of course. Yeah.
Well, it turns out Einstein might actually agree with that
Really?
for reasons that you would never expect.
I'm intrigued. So what does general relativity have to say about time flying when you're having fun?
Well, to start, I was really struck by how Rovelli emphasizes that general relativity is a field theory
Okay.
for gravity,
Mm-hmm.
similar to how we understand electromagnetism.
Yeah,
Can you kind of break down how that works?
absolutely.
Right.
Before Einstein, our understanding of gravity was based on Newton's idea of forces acting at a distance.
Right.
But Einstein completely revolutionized this by proposing that gravity isn't actually a force in the traditional sense.
Okay.
It's actually a consequence of the curvature of space-time itself.
Yeah.
And this curvature is created by the presence of mass and energy.
So instead of thinking about gravity as a force pulling objects together, we should think about it as objects moving along the curves
Yes,
of this warped space-time.
precisely.
Whoa.
You can picture it like a bowling ball on a trampoline,
Okay.
it creates that dip. And that's kind of analogous to what massive objects do to space-time. So other objects like planets or even light follow the curves of this warped space-time. And that's what we experience as gravity.
That is wild. It really changes your whole perspective
It
on
sure
something
does.
as fundamental as gravity. And Rovelli also mentioned that this means that Newtonian space and time,
Yes.
those absolute unchanging entities,
Mhm.
are actually part of a dynamic field, the gravitational field.
That's one of the key insights. Space and time aren't actually independent and absolute,
Oh,
but they're interwoven into this flexible, dynamic entity that we call space-time.
space-time.
Yes.
Okay, and it's this flexibility that allows for some incredible phenomena like time dilation.
Exactly.
Time dilation, hold on. That sounds straight out of science fiction. Does that mean time travel is possible?
Not time travel in the traditional sense, but time dilation basically means that gravity affects the flow of time.
Okay.
Clocks actually run slower in stronger gravitational fields. So you could imagine two identical clocks,
Mm-hmm.
one on Earth's surface
Right.
and another on a high-altitude satellite. The clock on the satellite would actually tick slightly faster
Really?
than the one on Earth because it's experiencing weaker gravity.
So time isn't a universal constant.
Right.
It's
Yeah.
relative to the strength of the gravitational field.
Exactly. And this has been experimentally verified numerous times. It's a direct consequence of general relativity.
That is wild. And this effect, as tiny as it is, even has real-world applications, right?
It says.
Like, I think GPS satellites?
Yes. GPS satellites need to adjust their clocks to account for time dilation to ensure accurate positioning.
That's amazing. So these, like, seemingly abstract concepts really do have tangible consequences. But I'm curious about the implications of time dilation for space travel. So, like, astronauts traveling at really high speeds, would they age differently?
That's a great question. And the answer is yes.
Okay.
The faster you travel through space, the slower time passes for you relative to someone who's stationary.
Wow.
It's called special relativistic time dilation.
Okay.
And it's actually a consequence of Einstein's special theory of relativity.
Oh, well,
It's a separate concept from the gravitational time dilation we've been discussing.
gotcha.
But they both highlight the flexible nature of time.
This is blowing my mind. So time is not only relative to gravity, but also to speed.
Exactly.
Einstein really turned our understanding of the universe upside down.
He really did.
Hmm.
And we've only just begun to explore the implications of his theories. Next, I think we should dive into one of the most intriguing phenomena predicted by general relativity: gravitational waves.
Okay.
These are ripples in spacetime caused by accelerating masses, similar to how accelerating charges produce electromagnetic waves.
Gravitational waves, okay. That sounds like something straight out of a Star Wars movie, but I thought light was the fastest thing in the
No.
universe. How can ripples in space-time travel?
That's a common misconception.
Oh,
While light does travel at the fastest speed possible within spacetime, gravitational waves aren't actually traveling through spacetime. They're disturbances in the fabric of space-time itself, where you can imagine it like dropping a pebble in a pond.
Okay.
Those ripples that spread outward
Yeah.
aren't really traveling through the water so much as they are distortions of the water's surface.
Okay, I'm starting to get it. So these gravitational waves are essentially distortions of space and time
Yes.
propagating outwards from accelerating massive objects.
Precisely. And just like light waves have different properties depending on their frequency, gravitational waves also have these unique characteristics.
Right.
For instance, unlike electromagnetic waves, which have a spin of 1,
Okay.
meaning they return to their original state after a 360-degree rotation, gravitational waves have a spin of 2, so they only need a 180-degree rotation to return to their original state.
So they're like a spinning coin that returns to its original state, either heads or tails, after only half a turn.
That's an excellent analogy.
Okay, and the thing that really blew me away is that Einstein himself initially doubted the reality of these waves.
He did.
Wait, really? The father of relativity wasn't convinced about one of his own theory's most mind-blowing predictions.
It happens. Science is a process of constant questioning and refinement,
Right.
even for brilliant minds like Einstein. But ultimately, his equations did predict them correctly.
Wow.
And it took a century for us to directly detect these waves in 2015.
Talk about a vindication. That is incredible.
It is.
So these gravitational waves are rippling through the universe. But what happens when the source of these ripples is incredibly massive, like a dying star? Could these waves become so intense that they warp space-time to an extreme degree?
That's a great question, and it leads us to one of the most fascinating objects predicted by general relativity: black holes.
Black holes,
Ah.
the cosmic vacuum cleaners.
Well, not quite vacuum cleaners,
Right.
but they are regions of space-time so warped that not even light can escape.
Is that true? Not even light.
That's right. It's formed when a massive star collapses at the end of its life cycle,
Okay.
concentrating all of its mass into an incredibly small region. This creates such an intense gravitational field that it warps space-time to the point where not even light, the fastest thing in the universe, can escape.
So it's like the escape velocity becomes greater than the speed of light.
Yeah, that's a good way to think about it.
Yeah.
And the boundary around a black hole beyond which escape is impossible is called the event horizon.
The event horizon.
Once you cross that line,
Right.
there's no turning back, at least according to classical general relativity.
Okay, I need a moment to let all this sink in. We've gone from time being relative to gravity and speed
Right.
to invisible ripples in space-time,
Yeah.
and now objects so dense that they trap light itself.
It's a lot to take in.
It's incredible. And a little terrifying.
It certainly challenges our everyday understanding of reality.
It really does.
But that's the beauty of general relativity.
Yeah.
It allows us to explore these realms of the universe that were once unimaginable, pushing the boundaries of human knowledge.
Yeah, and forcing us to reconsider the very nature of space, time, and gravity. This has been an incredible start to our deep dive.
It has.
But before we venture further into the mysteries of black holes, I'm curious about the singularity at their center.
Right.
Is it really a point of infinite density where the laws of physics just break down?
That's a great question.
And is there any possibility of escape even from a black hole?
Those are great questions, and they point towards where general relativity meets its limits
Okay.
and where the need for a deeper theory, quantum gravity, comes in.
Quantum gravity. All right, so that's a story for part 2 of our deep dive.
Stay tuned.
I am hooked. Listeners, stay with us for part 2 of our journey into general relativity, where we'll continue to unravel the mysteries of black holes, explore the mind-bending possibilities of quantum gravity, and perhaps even challenge the very nature of time itself.
It's going to be a wild ride.
Welcome back to our deep dive into general relativity. Last time, we really explored how Einstein's theory revolutionized our understanding of gravity, space, and time.
It was quite a journey.
It was a wild ride. We learned about warped space-time, time dilation, gravitational waves, and even those mysterious objects called black holes.
Right, and we left off on the question of what lies at the heart of a black hole.
Right.
The singularity, and whether it's truly a point of infinite density where all known physics crumbles.
Yeah, exactly. And you hinted that the answer might lie in a deeper theory. Quantum gravity.
Yeah.
What exactly is quantum gravity?
Okay.
How does it relate to general relativity?
Quantum gravity is one of the biggest questions in physics today.
I bet.
It aims to bridge the gap between general relativity,
Okay.
which describes gravity as the curvature of space-time,
Right.
and quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels.
So it's like the quest for a unified theory that can explain the universe at all scales.
You got it.
Okay, from the smallest particles to the largest cosmic structures.
Yeah. The challenge is that these two theories seem almost incompatible.
Oh.
General relativity views gravity as this smooth, continuous force acting on this smooth space-time fabric, while quantum mechanics describes the world as fundamentally discrete and probabilistic, with particles behaving like waves and interacting in these quantized ways.
How can something be both smooth and chunky at the same time?
Right. It's a puzzle.
It's a head-scratcher.
And that's where the idea of loop quantum gravity fits into all of this.
Okay, loop quantum gravity.
Yes.
What is that?
So loop quantum gravity is one of the leading contenders in the search for a theory of quantum gravity.
Okay.
And it suggests that space-time itself, at its most fundamental level, isn't actually smooth and continuous, but rather woven together from these tiny interconnected loops.
They're in a connected loop.
Yeah, imagine like a fabric made of threads, except these threads are loops of pure geometry.
Okay, so instead of picturing space-time as a smooth trampoline, we should imagine it as this network of interconnected loops.
Exactly.
That sounds pretty radical.
It is. And it means that space-time has this granular structure, like pixels on a computer screen.
Pixels?
At the Planck scale,
Okay.
which is about 1035 meters. That's far smaller than anything we can currently observe.
So at these incredibly tiny scales, the very fabric of reality becomes quantized.
Yes.
Meaning it comes in these discrete chunks. And this has profound implications for our understanding of black holes, right?
It does.
So like how classical general relativity predicts a singularity at the center of a black hole, a point of infinite density where the laws of physics break down.
Right, right.
That always seemed a bit too bizarre to be true.
Well, loop quantum gravity offers a different picture.
Okay.
It suggests that the singularity might not actually be a point of infinite density, but rather a region where the quantum nature of space-time becomes dominant. So instead of collapsing endlessly, the matter inside a black hole might reach a point of maximum compression.
Okay.
And then...
And then what? Does it just stay stuck there?
Here's where things get really interesting.
Okay.
Some physicists believe that this extreme compression could trigger a quantum bounce.
A bounce.
Similar to what we discussed with white holes. Instead of collapsing into oblivion, the black hole could rebound outwards, potentially even transforming into a white hole.
A white hole? You mean a region of space-time where matter and energy are spewing outwards?
Yes.
Almost like a reverse black hole.
Exactly.
Yeah.
While black holes are defined by their event horizons, those points of no return, white holes are theorized to have these exit horizons.
Exit horizons.
Which are boundaries beyond which nothing can enter. It's as if the black hole turns inside out, becoming a source of creation, rather than a cosmic sinkhole.
Okay, so what falls into a black hole might eventually emerge from a white hole somewhere else in the universe.
It's possible.
Or even in another universe.
Maybe. Who knows? It's a wild idea.
That's crazy.
But it highlights the strange and wonderful possibilities that quantum gravity opens up. Now, white holes remain hypothetical.
Right.
But they arise naturally from the mathematics of general relativity when you consider time reversal.
Okay.
And loop quantum gravity provides a possible mechanism for their formation through this quantum bounce at the singularity.
So we're talking about a potential cycle here.
Yes.
A star collapses, forming a black hole, which then undergoes this quantum transformation at its core, potentially leading to the birth of a white hole, spewing matter and energy back into the universe.
Yeah, it's like a cosmic recycling process.
It really is. And this idea of black holes evolving into white holes has profound implications for the nature of time itself, right?
Right. Remember how we talked about time dilation? How time flows differently depending on the strength of the gravitational field?
Yeah, and how it affects GPS satellites and even aging.
Well, inside a black hole, as you approach the singularity, time dilation becomes extreme.
Okay.
From the perspective of an observer outside the black hole, time would appear to slow down infinitely as an object falls in, essentially freezing at the event horizon.
So from our perspective, nothing ever truly falls into a black hole.
That's right.
It just gets stuck at the edge, forever frozen in time.
That's how it would appear to us. But from the perspective of the object falling in time would continue to flow normally.
So whose perspective is correct?
Well, that's the beauty and the challenge of relativity.
Yeah.
Both perspectives are valid, depending on your frame of reference.
Okay, so time really stops. or it keeps going. It depends.
Right, but the possibility of a black hole transforming into a white hole
Yeah.
raises even deeper questions about the arrow of time. If what falls into a black hole can emerge from a white hole,
Mm-hmm.
does that mean time can flow in reverse?
Time flowing in reverse? That sounds like something out of a science fiction movie.
It might sound strange, but it's a question that physicists are seriously considering.
Really?
Yes, some theories suggest that the arrow of time,
Oh,
the direction in which we perceive time flowing,
right.
might not be a fundamental law of nature,
Okay.
but rather a consequence of the initial conditions of the universe.
So the direction of time might not be absolute.
Potentially.
It could be different in different parts of the universe, or even reverse under certain conditions.
It's a mind-bending concept, and it's one of the many mysteries that quantum gravity might help us unravel. This connection between black holes, white holes, and the arrow of time is a frontier of physics, full of intriguing possibilities and profound implications.
This is incredible. We've been on this whirlwind tour of the most extreme and mysterious objects in the universe.
We have.
From collapsing stars to the potential for time reversal.
Yeah, it's been wild.
I'm curious, though, are there any hints of these quantum gravity effects
Mhm.
that we might be able to observe in the universe today, or is this all just theoretical speculation?
That's a great question. While direct observation of quantum gravity phenomena is incredibly challenging due to the tiny scales involved,
Right.
there are some tantalizing possibilities.
Okay, what are those?
For example, some physicists believe that quantum fluctuations in the fabric of space-time
Right.
might be amplified by strong gravitational fields, like those around black holes or in the very early universe.
Amplify, you mean like those tiny ripples in space-time? The gravitational waves could carry a signature of the quantum nature of gravity.
Exactly. It's a long shot.
Okay.
But future generations of gravitational wave detectors might be sensitive enough to detect these subtle signatures.
Wow.
Other potential avenues for observing quantum gravity effects include studying the cosmic microwave background radiation,
Right.
the afterglow of the Big Bang,
Mm-hmm.
for tiny imprints of the quantum nature of space-time in the very early universe.
This is so exciting. It's like we're on the verge of a new era of discovery, where we might finally be able to glimpse the quantum workings of gravity and unlock the deepest secrets of the universe.
I agree. The quest to understand quantum gravity is one of the most ambitious and challenging endeavors in human history.
Yeah.
It requires us to push the boundaries of our knowledge,
Mm-hmm.
challenge our most cherished assumptions,
Right.
and to embrace the unknown with curiosity and wonder.
Before we continue our journey into the realm of quantum gravity,
All right.
I want to touch on a point you made earlier about the need for a theory that can explain the universe at all scales. We've been focusing on the extreme cases,
Yeah.
black holes and the Big Bang.
Mm-hmm.
But does quantum gravity have any implications for our everyday lives?
That's an excellent point. While the most dramatic effects of quantum gravity likely manifest themselves in the most extreme environments,
Okay.
its principles could ultimately impact our understanding of physics at all levels, potentially leading to technological advancements that we can't even imagine yet.
So could you give us some examples of how quantum gravity might affect our lives in the future?
It's hard to speculate on specifics,
Right.
but just imagine harnessing the power of quantum gravity to manipulate space-time itself.
Okay.
It could revolutionize space travel, allowing us to warp space-time and travel vast distances in an instant, or even open up gateways to other dimensions.
Oh.
It could lead to new forms of energy generation, tapping into the quantum fluctuations of space-time itself. The possibilities are truly mind-boggling.
Now that's a future I'd love to see.
Yeah, it'd be amazing.
But for now, let's return to the present and continue exploring the incredible insights that general relativity and quantum gravity are already providing. We've talked about black holes, white holes, and the arrow of time. But there's one more fascinating aspect I want to touch on: the Big Bang.
Ah, yes, the ultimate origin story. In part 3 of our deep dive,
Yeah.
we'll delve into how loop quantum gravity offers a new perspective on the Big Bang,
Okay.
proposing a scenario where the universe didn't begin with a singularity,
Mm-hmm.
but rather with a big bounce.
Big bounce. It sounds like the universe has some serious trampoline skills. I can't wait to hear more about that.
It's a fascinating concept.
Listeners, join us for the final part of our deep dive, where we'll explore the quantum origins of the universe, the nature of reality itself, and the incredible possibilities that lie ahead in our quest to unravel the mysteries of gravity and spacetime. Welcome back to the final part of our deep dive into general relativity and quantum gravity. It's been a wild ride, hasn't it?
It certainly has. We've covered a lot of ground.
We've journeyed through warped space-time, encountered those mysterious black holes and white holes,
Right.
and even contemplated the very nature of time itself. But now we're going to tackle the biggest question of all, the origin of the universe.
The grand finale.
Yes, the Big Bang. It's the prevailing model for how everything began.
Hmm.
But you've hinted that loop quantum gravity offers a whole new perspective on this cosmic event.
Absolutely. You see, when you apply classical general relativity to the Big Bang,
Okay.
it leads to a singularity, a point of infinite density and temperature, where the laws of physics, as we know them,
Yeah.
just break down. It's always been a bit of a puzzle for physicists, a point where our theories hit a wall.
So just like with black holes, the idea of a singularity at the Big Bang feels kind of incomplete. Like there's something more to the story.
Right, and that's where loop quantum gravity comes in. Remember how we talked about space-time being woven from these tiny loops at the Planck scale?
Yes, like a cosmic fabric made of these interconnected threads of geometry. It's a pretty wild idea.
It is.
Yeah.
But when you apply loop quantum gravity to the very early universe, it suggests that the Big Bang might not have actually been a singularity, but rather a big bounce.
A big bounce. So instead of the universe exploding into existence from a single point,
Right.
it was more like a rebound from a previous phase of contraction. Like the universe was collapsing.
Exactly.
And then it bounced back out.
Imagine the universe collapsing under its own gravity,
Yeah.
reaching this incredible density.
Okay.
But then, instead of collapsing into a singularity, the quantum nature of space-time kicks in. Those tiny loops actually prevent further collapse, leading to a rebound, an expansion, the Big Bang as we know it.
So instead of a beginning, there was a transition.
Yes.
A bounce from a previous phase of the universe. That completely changes our picture of the cosmos. So the universe has been through multiple cycles of expansion and contraction, like a cosmic heartbeat.
It's a revolutionary idea, and there are mathematical models in loop quantum cosmology that support it.
Wow, that is mind-blowing. So we've gone from questioning the very nature of space and time
Yeah.
to reimagining the origin of the universe. It seems like loop quantum gravity isn't just about quantizing gravity, but about rethinking some of our most fundamental assumptions about reality itself.
You're absolutely right. It's a shift in perspective, from seeing the universe as a stage upon which events unfold to understanding it as this dynamic interplay of quantum fields and geometry where space and time themselves are emergent properties.
This whole deep dive has been incredible. I feel like we've jumped into the deep end of physics and come out with a whole new understanding of the universe.
I'm glad to hear that.
But before we wrap up, I want to bring things back down to Earth for a moment. What are some of the practical implications of quantum gravity?
Okay.
Like, how might this impact our lives in the future? I know it's still early days, but is there anything we can speculate about?
Well, while quantum gravity is still largely theoretical, its potential implications are vast. Imagine, for example, harnessing the power of quantum space-time to create new technologies. We might one day be able to manipulate gravity, warp space-time for interstellar travel, or even tap into the quantum foam for energy generation.
Okay, those sound like scenarios straight out of science fiction. But it's exciting to think about, right? What seems impossible today might be possible in the future, thanks to our growing understanding of the universe.
Exactly. The pursuit of knowledge, especially in fields like quantum gravity, is about pushing those boundaries, what's possible, and shaping the future.
It's been an incredible journey, exploring these mind-bending concepts, challenging our intuitions, and I think catching a glimpse of the profound beauty and mystery of the universe.
I agree. It's been a fascinating exploration.
And it's really left me with more questions than answers, which I think is a good thing.
It is.
It means there's so much more to discover, so much more to learn.
Absolutely. The quest for understanding is never ending. There's always more to discover, more to question, and more to wonder about.
On that note, I want to thank you, the listeners, for joining us on this deep dive. We hope you've enjoyed the journey as much as we have. And until next time, keep looking up at the stars and pondering the mysteries of the universe.